Hello everyone, welcome to Tan45Engineering. We are here with yet another video in our mastering data structures and algorithms in Java. Today's topic is space complexity. Let's start. So we already understand asymptotic notations. We understand what is time complexity. Similarly, space complexity is important as well, right? So we'll understand what is space complexity and how do we calculate it. So what is space complexity? Space complexity measures the amount of memory an algorithm uses as a function of the input size. It includes both the memory used by the variables in the algorithm and the memory required for the input itself. Why is space complexity important? Because it helps us in evaluating how much memory an algorithm requires, especially when working with large data sets. It is also essential for optimizing programs to prevent excessive memory usage. Also, many times it would happen that you have an algorithm that is very efficient in terms of time complexity, but very bad in terms of space complexity. So when you are making a decision, you might go move to an algorithm which is not so good in time complexity but saves you a lot of space as well. So based on your requirement, you choose an algorithm and you weigh them in time complexity as well as space complexity. Space complexity is actually very easy to calculate. We only have to focus on two parts. One is the fixed part, that is memory required by the variables, the constants, and the code itself. It does not change with the input size, so you can always consider it constant for the given equation or problem. Variable part, actually it depends upon the algorithm that you use. Memory required by dynamic data structures. So let's say your solution is to sort an array in memory. So let me explain this. So I'll edit it 1 second. Okay, so this is space complexity. Okay, so let's say you have an array and 1 2 4 3 and you have to sort this array. So maybe you use another array first, one by one you take out the smallest element, you copy it 1, you traverse through, you found the next smallest element 2, then traverse, find the next smallest element 3, then again and then 4. Or you traverse in the same array and check 1 is at its correct place, 2 is at its correct place, 4 is here but 3 is smaller, so you swap 3 with 4. To make the swap, maybe you use another variable called temp, right? But now you are doing in memory sorting. So it will become 4 will get shifted, 3 will come here, and 3 will get removed from here, and 4 will come here. You did not require another array. If you would have required another array, O of n space complexity would have increased. But for in-memory algorithms, you're not increasing the space, right? So this is the difference when you are using an algorithm to calculate space. Okay. So that's the variable part that changes with the algorithm. So in case of first algorithm, we are doing in-memory sorting. We are not using extra space. In second algorithm, we are using another array to sort this. So the time complexity of the first algorithm would be O of 1 constant. For second one, it will be O of n. But this is space complexity, not time complexity. Okay, space complexity. So once you understand time complexity, space complexity is very similar. So you have already seen that from the first video. Okay, now let's move to different types of space complexities to understand. So one is constant space. Like in this example, we just have to swap the elements in A, B. We are taking another variable. So the algorithm uses two fixed amount of memory regardless of the input size. We always use A, B and temp, right? And then we swap the elements. A and B is always used, temp is used for temporary, and the sorting is done. If the input size increases also, we are still making the swap between two elements only, so that space complexity will always be constant O of 1. Next we have linear space. So the memory usage grows linearly with input size. Example, storing elements in an array list. So you have a method create array and it is returning a new array, and the array is of size n. So if the size of the input n increases, the returning array size will increase as well, right? If we have asked for 2, we'll return an array of size 2. If n is 10, array of size 10 will be created and returned, right? So in this case, the space required increases with the value of n. So it is linear to the value of n. It's a linear space complexity. Similarly, let's move to the next one. This is quadratic space complexity, as you can understand it clearly from the example. Since we are returning a 2D matrix and the matrix depends on the value n, it is a n raised to the power 2 space complexity. So if the, let's say, the size of n was equal to 1, we'll return this. N is equal to 2, will return with 4 values to come, right? If n is equal to 3, we'll return a 2D matrix that has 9 values, right? So the size of the space is increasing based on the value of n in the multiple in the n square power. So for 1 it was n raised to 1 raised to power 1, it is 1. For 2 it is 2 raised to power 2, it is 4. For 3 it is 3 to power 3, the same. Okay, oh sorry, 3 to power square, and 3 into 3, 9. For 2 to power square, 2 to 4. 1 to power square, 1 is 1. Okay, so that's why n raised to power square. It's a quadratic space complexity. Next we have logarithmic space complexity, log of n. So it can happen when you have to perform recursive algorithms, or majorly when you have to perform recursive method callings in any algorithm or in stack, right? So the memory usage grows logarithmically with the input size. In this case of binary search also, binary search always comes with log n in terms of space complexity and time complexity. Also, you have to understand that when you have a method, let's say you have a method function 1, and inside function 1 you are calling function 2, inside function 2 you are calling function 3, and inside that similarly, right? So you create a stack in the memory, a memory stack gets created. It has the context for the first one, then it creates another stack based on the second function, then it creates another stack based on the third function's requirement, saves all the variables and everything required by the third function. This one will save everything required by the second function and context to the third one. Similarly, the first one will save everything here. So the space requirement for this function will keep on increasing, right, based on value of n. So this happens when we make stack functional calls, right, or it's very common in recursive calls. So similarly, for logarithmic space complexity, binary search is one example where the space is increasing logarithmically to the given input n. Next, how to analyze space complexity? So it is very simple. We have to focus on two components. One is the fixed part. Okay, count the memory used by the variables and the data structures. Analyze how memory scales and input size. So if you want to calculate exact to the bytes, you calculate it for int size, float size, integer, string size, and then we have to include the dynamic data structures that are getting created. In recursive algorithm, account for memory used by the call stack as well, as we just discussed. In a function 1 we are calling the second function, then third function, fourth function. So in recursive calls, the space will increase in this manner. Calculating space complexity is very simple. Okay, so let's say we had a for loop, or we are doing anything. In the end, we need to sort, we need to create another array of size n. We are using some variables, variable 1, 2, 3, 4, so size of all the variables, and let's say this type is int, and similarly int is the type of the array. So you calculate these sizes, you calculate the size for one integer and then multiply it by n. Again, it is dependent upon n, and this part c. So c is constant, so we'll always take space complexity as O of n. So calculating space complexity is similar as calculating time complexity. Please go through the time complexity video to make it more clear for you. In the end, understanding space complexity is as important as understanding time complexity. So then now you can weigh your algorithm not only in terms of time complexity, that this algorithm is faster, but also in terms of space complexity, that this algorithm takes or requires less space on your memory. This is very helpful. Okay, so that's all from today's video, everyone. For anything, if there are any doubts or questions, please let me know in the comment section. In the end, thank you everyone. Please like, share and subscribe.